Today we're going to be talking about nutrient availability and uptake and how we can use our lab results to better understand the soil dynamics and the uptake patterns that we see in our field so we can know exactly where to put our fertilizer dollars. My name is Jack. I'm the CEO and founder of Cultra, a nutrient analytics software for growers and crop consultants. We're going to break down the spectrum of availability that our nutrients go through, presence, the nutrients in the soil. Then that nutrient needs to be mineralized, turned into the correct form where it can enter into the soil solution to then be taken up by the plant. Each step on this spectrum can be tested using lab tests. Things like a standard soil test, or a Haney test, or a plant sap test, or a PLFA test. All of those are tools in the toolbox to figure out where your nutrients are on the spectrum. And then we can make fertilizer decisions to systematically unblock where our bottlenecks are. Oftentimes these bottlenecks are going to be in key points going from presence, so in the soil but not available, to in the soil and available, to actually getting taken up by the plant. The issue is each of these tests individually doesn't tell the entire story, meaning we don't have enough information to systematically know where exactly our best management decision should be on this spectrum. So in this video, we're going to go over a bunch of examples on how we can use these lab tests that are coming onto the market or have been on the market for a while to really figure out and dig deep on where that bottleneck is. Because if you rely on only one of these tests, you might be missing the whole picture. And we might be only addressing a symptom of a root cause, or trying to address a root cause, but without knowing the full picture, we might be creating downstream antagonisms and further impacting our nutrients availability to go from just being present in the soil to being available to our plant. And this uptake piece is going to be the ground truth data that tells us how good we are doing at managing our nutrients along this spectrum. First, I'm going to just define a couple of these terms. So presence, that means there's nutrients in the soil. They may not be available, but they're in the soil. We're going to use a couple lab tests to figure out, are the nutrients even there in the first place? Because it doesn't matter if they're, in the correct form, if we're doing something like a Haney test. If they're not there in the first place, we can't mineralize them. We're gonna look at things like a standard soil test or a total nutrient digestion to figure out this piece. If we only did this type of testing though, we would not have a full picture and we wouldn't know if our bottleneck is here or further down this line, preventing uptake. So it's important to start here just to get a baseline understanding of where your soil is. With these types of tests, we can measure things like soil texture and CEC to figure out what we're working with. How many nutrients can our soil actually hold? That information is key for influencing what levers we can pull to unblock downstream effects. But these aren't the full picture. Closer to a full picture is going to be something like a Haney test. A Haney test is still not going to be a full picture because we don't know if it's actually getting into the plant. Even if it's in the correct form, there could still be issues with getting that nutrient that's in the correct form getting uptaken by the plant. Could be things like irrigation, could be things like nutrient placement, where you took your samples. There are always going to be key issues with looking at just one test without seeing the full picture. But tools like the Haney test can point us in the right direction because we can look at mineralization rates through our water extractable organic carbon levels or our soil respiration levels, which tell us how good our soil engine is at getting nutrients from presence to the correct form. Sometimes if any test biological levels are low, this transition from going from presence to the correct form, that could be our bottleneck. And if that's our bottleneck, it's going to be really difficult to get it uptaken by our crops. I also want to mention the PLFA test. So the Haney test measures proxies for biological indicators. Soil respiration rates, for example, measure the amount of carbon dioxide that's accumulated, so how well your soil's breathing, which is a proxy for the amount of microbes that are in your soil. The PLFA test tells you how many microbes are in your soil in the broad categories of what those microbes are. For example, we know that for a perennial operation, we want to have a higher fungal to bacterial ratio than in a row crop annual. And a PLFA test can help guide us, letting us know which levers we should pull to make this arrow right here to go from presence to correct form best suited for our operation. The Haney test not only measures the biological proxy indicators like water extractable organic carbon, which is microbial food, or soil respiration, a proxy for the amount of microbes that are in our soil. It also measures the nutrients that are available in the soil solution more closely resembling what our current availability is looking like, using a weaker acid than something like a Mylic 3 or a total nutrient digestion. When we use a weaker acid, we're more closely simulating what the plant is experiencing when the plant is exuding weak acids to unbind nutrients into the soil solution to be uptaken. So we get the biological indicators and a list of our standard nutrient indicators like our nitrogen, phosphorus, potassium, macros, and micros. We see those nutrient levels both in this present section and in this correct form section. Generally, it's going to decrease as we go from present to correct form because we don't want all of our nutrients to leach away. If all of our nutrients were in the soil solution, if we had a heavy rain event or heavy irrigation event, they're not going to be bound to our soil, meaning they could leach away and then we would have to replace all of them. So we want our nutrients to be in this presence category. It's kind of like our savings account, and this is closer to our checking account. That's key to understand because we want to make sure that we are moving our nutrients from the presence to the correct form when our crop needs them. Having our nutrients locked in the soil prevents them from getting leached away. So neither of these is good or bad. It's just giving you the information to know maybe there's a bottleneck going from presence to correct form. Now, what does that look like chemically in the soil? So here we have a calcium phosphate molecule. This cannot be taken up by the plant, so therefore it's not in the correct form. When we apply a strong acid to this calcium phosphate molecule, it breaks up into the ionic form, calcium and phosphate, which can be taken up by our crops. And so this difference, the delta between what we have and what our plants can potentially use, is helpful to understand. It's helpful to have a couple tools in your toolbox to know where those levels are. Now we're going to talk about uptake. This is the only way that we can figure out ground truth about what's happening in our crops. And generally, we're going to look at plant sap analysis. I know plant sap analysis can be really difficult. For almonds, for instance, I've heard it takes a ton of man hours to collect all of the leaves in order to do it. But we're going to be talking generally about plant sap analysis here because it is the closest to real truth we can find when we're talking specifically about using lab data to understand our nutrient uptake patterns. We can also look at tissue tests. The issue with tissue tests is sometimes they can be wrong. Sometimes you can have super high iron levels on a tissue test and it's just because of a contamination. It might not always be accurate for every single nutrient. It also doesn't tell you what's happening in the plant like plant sap analysis does. But if plant sap analysis is not available for you or your operation, a tissue test is a good replacement, better than nothing. The reason is we want to figure out what nutrients are getting into the plant. And if we're using plant sap analysis, we can oftentimes make corrective measures before they impact yield, whereas tissue analysis generally tell us what are our crops able to get, so next season we can fix one of these bottlenecks and make sure that a deficiency doesn't happen again. But with plant sap analysis, we can solve that deficiency in season. So that's why that's preferred. But I know there are a lot of limitations like cost and labor hours in order to get the necessary samples. But if you can, this is our ground truth. Going back to this example, we have the calcium phosphate going into a calcium ion and a phosphate ion. And then the key thing we're going to look here with uptake, we're looking at, can we turn the nutrients into biomass? It doesn't matter if our plant pulls up a bunch of nutrients if it's not actively using those nutrients in our crop. In a plant sap analysis, we can see, do we have things like free nitrate, right? If we have high free nitrate levels, we're pulling in a bunch of nitrate in the correct form, but sometimes it's not getting assimilated into proteins, meaning it's not turning the fertilizer dollars that we're spending into actual biomass, which is what we spend our fertilizer dollars on, is turn that fertilizer into yield. And so if we're pulling up a bunch of nutrients, but they're in the free nitrates, they're not turned into proteins, then we can have issues. And so plant sap analysis can show us that. And so here what I'm going to write are proteins, because the proteins are what the nutrients make. we pull up the nutrients so they can bind with each other in the plant, be used for specific plant functions like amino acids and proteins and cell walls and everything our plant needs to turn sunlight into sugars to create this engine of growth. So this is our overview. It's kind of a mess, but again, we have presence. Is the nutrient available in our soil? Is it in our soil in the correct form that our plants can uptake? Did our plants actually uptake those nutrients? And we can use a suite of tests. If we look at any of these tests individually, we miss the entire picture. If we look at just a Haney test, we might not know if we should apply a granular fertilizer or a foliar application. If we look at just a plant sap analysis, maybe the issue is we have a nutrient antagonism that's going on, where we're applying excess of one nutrient and it's causing an inhibition of another nutrient. And so we may do another fertilizer application where we're doing an excess of one that's causing an inhibition of another. So then we're double applying fertilizer instead of reducing the inhibition causing nutrient. And so if we can take all of this data and we can figure out where the key bottlenecks are, what's preventing us from going from having a high amount of a nutrient in our soil, but having a low amount of the nutrient in the correct form, maybe we need to focus on the mineralization rates. Maybe we need to increase our soil's biological engine by adding things like humates and other carbon sources. But maybe we have a bunch of the nutrients in the correct form and none of them are getting uptaken. Maybe it's just an irrigation issue. Our roots can't pull in the nutrients in the soil solution because we're not irrigating at a high enough frequency. Our nutrients can't move through the water into the roots. Or maybe that soil is compacted and it's all three. Maybe we have a high amount of something like magnesium, but it's too high, it's tightening our soils, preventing our roots from being able to break through and go as deep as they can. But our nutrients look like they're all in the correct form, they look fine, but we can't uptake them because of an issue that's all the way over here in a standard soil test. So now that we kind of understand what we're talking about, the different tests we're talking about, I'm going to go through specific examples of where we can use a holistic data-driven approach to figure out where our bottlenecks are and how to correct them. All right, that was a lot of information and somebody on the internet might yell at me for something I said. Apologies if I didn't get your specific operational needs exactly correct. I'm synthesizing information from the hundreds and hundreds of agronomists that I've talked to over the past year or so to understand how the agricultural industry as a whole is changing on fertilizer decisions. As fertilizer prices are increasing, we're trying to figure out how can we farm the most efficiently. And it's my understanding that a data-driven approach in combination with as many tools in the toolbox with as little dogma as possible is the correct answer. So if anything I said here doesn't apply to your specific operation, I apologize. I'm just synthesizing information from the thousands of experts that I've been lucky enough to have talked to. All right, so now we're gonna go through our case study. None of this is real. Ideally, I'd like to be out in the field being able to do this with real data, but right now we're just coming up with a couple ideas of where maybe we have different levels across these tests from presence of that nutrient to the correct form to the truth, which is it being uptaken by the crop. If we looked at each of these tests individually, we wouldn't be able to get the full picture to know exactly where our bottlenecks are. So that's what we're going to do right now. So we look at a soil test and our pH is fine. That's not going to be an issue, 6.5. CEC is medium, 15, so that means we can hold not a high amount, but a decent amount of cation exchange sites where that's not going to be our key limiting factor. Our potassium levels are adequate, our calcium levels are good, and our base saturation ratios, ideally we want this magnesium level to be slightly lower. Maybe if we have a 25% magnesium base saturation, we could see tightening of our soils and an increase of compaction. So that's going to be the one thing we're looking at on this soil profile. I know the people in the northwest area are going to say, well, my magnesium is really high and that's completely fine. If that's the case, I'm not talking to you. A lot of times, if you see magnesium levels that are higher than a normal ratio, it could be reducing your soil's ability to create good structure in aggregates. If you watch our earlier videos on calcium or magnesium, the actual ion, the magnesium and calcium ion, are at different sizes when they're hydrated and create either aggregation and flocculation or dispersion, which causes compaction. So that's why we're going to be talking about this magnesium guy right here. So magnesium's at 25%. We're going to look at that, flag that in our head. Maybe we're going to see some limited nutrients moving through the soil solution because it's harder and slower for nutrients to move through compacted soil that is dispersed rather than aggregated and flocculated. So that's the one thing we're going to look at here. But this is not the truth. We don't know if our potassium is getting into our plant. But if we look over at our SAP test that we took mid-season, potassium young leaf, mid to low, potassium is low. If we're going into a reproductive time, this potassium reserve in our old leaf, that's not good. We're flagging that. So what is the bottleneck between these? It may be here, but that could be a long-term fix, and it wouldn't really be economical to fix in one season, or even possible, especially on high acreage. But when we look at our Haney test, we've got these two indicators that I'm going to be talking about mostly for the rest of this video: the respiration rate and our microbe food, which is water extractable organic carbon. There's also water extractable organic nitrogen, and the ratio of those two determine what our potential microbial population could be. And our potassium levels, so our correct form of potassium, is in the mid to low range. Not generally, big cause for concern, but it is when our SAP is low. We're going to be taking all of this in, and we're looking at potassium, right? What can we do to prevent our plant from undergoing a potassium deficiency stress if we've taken a plant SAP and our potassium is low to mid-low? Now, a couple things. First, what we talked about here, our potassium looks good. It's in the soil, right? Our potassium is in the soil. Most of the time, the nutrients are in the soil, but we want to check, because if our nutrients aren't in the soil in the first place, then we should add them. The second thing we want to look at that could be closer to our actual bottleneck are these right here. Now, if we have a low amount of microbes, then we have a low mineralization rate, which is turning this potassium, which is bound tightly to our minerals or organic matter, into the available potassium, which eventually our plants are going to be grabbing. If we're able to raise our carbon levels, then we can raise our respiration levels. If we can give our microbes more food, our microbes are able to grab more of this potassium and put it into this zone, which ideally will bring it over to the sap. But if we look and our soils are fairly compacted because we have a low amount of flocculation that's happening due to tight soils with a high base saturation of magnesium, then it might not be something that can be fixed in just one season. It often isn't. So we want to figure out, what do we do now, and what do we do 1 year from now, 2 years from now, 3 years from now, to make it so we can decrease our input costs, decrease the amount of things that we have to do to provide any fixes. Because that's the entire goal. We want to make our soils a well-oiled machine that gives our nutrients to our crops exactly when our crops need them. Now, the other thing that I want to look at is this nitrate levels being high, and the reason for that is potassium plays a key role in nitrate assimilation, along with other nutrients like sulfur and iron and manganese, turning these nitrates into biomass, turning them into the proteins that our plants can use to create new growth. What do we do? It's already the middle of the season. We've got low potassium levels, and if we enter into a period where we're going to have rapid potassium uptake, we need our plants to be ready. So maybe we do something like a foliar application or a fertigation application, depending on your operation size and what you have available in your toolbox. But fixing it mid-season is probably going to be our best bet, because again, the sap is the truth, and it lets us know what we can do to prevent yield loss. Now we're going to talk about what we can do to make sure next season we don't run into the exact same issue, but worse. Applying something like a humic or fulvic acid to increase our water extractable organic carbon levels, in addition to making sure everything in our sap is functioning the highest that it can. So maybe some in-season foliar applications to help our microbes that are in our soil by giving them more sugars. If we can fix a lot of our issues with foliar applications this season, then our plants can pump more sugars into the ground, then we don't have to spend as much money on fixing this because our plants are doing it for us. Kind of a combo move is we can hit it to make sure we don't get a big decrease in yield from a massive potassium deficiency, and looking at increasing these guys for next season by applying some kind of carbon-based amendment. And then maybe over time, we're looking at displacing some of these magnesium ions to loosen up our soil. And because our pH is good, we probably wouldn't use lime. That would probably be bad. So maybe something like gypsum, if you look at your sulfur levels or something like that. And we can try and displace these magnesium ions to drop this down and hopefully loosen up the soil a bit. And that's all in addition to other long-term practices. Cover cropping and keeping our living roots in the ground, so we're pushing more carbon into our soil, right? Maybe instead of applying those humic and fulvic acids like we talked about, we do a cover crop at the end of the season to pump more sugars, more carbon into our soil to raise these numbers, to make this potassium go from just being present to being more available because we have faster nutrient cycling by microbes. But there's a host of tools that you have in your toolbox to fix these. It's just, what do you want to do right now that would be most efficient, not only this season, but for the next 5 years? So we don't make a problem worse, we incrementally get it to a place where you no longer have to worry about these. You no longer have to put more and more fertilizer down. You're putting less and less because you're unblocking the bottlenecks. That was a lot of information. I don't know if I got all of it right, but hopefully the overall principles make sense on how we're looking at using data-driven agronomy to find the bottlenecks instead of just doing blanket applications or blanket prescriptions. And we can use these lab results to figure that out. All right, example number 2, we're going to be talking about zinc. All right, kind of similar context. This time we're adding in organic matter, and I'll explain why in a sec. So in our soils, our pH is good. It's probably not going to cause any kind of availability issues at a level, or even on an organic matter level. 2.2 is fine, and we have a decent amount of parking spots for our nutrients. The issue we're looking at is this imbalance, right? Our phosphorus levels are generally higher than we'd like them to be in relation to our zinc levels, and that could be the case for why our sap zincs are low, because that zinc to phosphorus dynamic can prevent zinc uptake. Now, what's a multifaceted data-driven approach to fixing this? Let's first think of a couple tools we have in our toolbox, right? One, we should be taking our soil tests and looking at our phosphorus levels over the past few years. So you can upload them into Cultra and see, is this number going down or is it going up? If it's going up, it's probably trending in the wrong direction and making this antagonism worse. If it's going down, then we're should be in good shape depending on the slope of that line. Now, when we look at our nutrients that are closer to being uptaken by the plant, they're in the more available form, we have low zinc levels here. And so increasing our total amount of nutrient cycling, our ability of our soil to turn nutrients from this section into this section, we're going to need to increase overall carbon levels. So that can be done either by increasing our plant's ability to pump carbon into the ground, which would be like fixing, if you follow John Kemp's videos, I think it's like stage 1 of his pyramid, using foliars to get your saps correct for certain nutrients to pump more sugars into the ground, or applying carbon-based amendments like humic and fulvic acids to increase our food that our microbes can eat to increase the amount of microbes we have. We included the iron and manganese levels just to check to make sure it's not a full contextual micronutrient issue, which it could be if pH was something like 7.4, right? Then we could see like zinc, iron, and manganese all low. That would be a problem. We'd probably want to address that in a different, multifaceted way. But because this iron and manganese levels are good, we're probably going to address something slightly different. Maybe just raising our zinc levels could do it. Maybe raising our zinc levels over a couple years while doing 1 or 2 years of foliar applications, knowing that we have low zinc availability. While we're fixing our phosphorus to zinc ratios, we're increasing inoculants and decreasing just general MAP or DAP applications. All of those kind of in conjunction, talking to your local crop advisor and your local agronomist, or if you are a local crop advisor, local agronomist, figuring out like exactly what. But all of this data in conjunction can provide a fuller context to know exactly which amendments we should be applying. In addition to knowing just a snapshot of what's going on, we want to be making sure we're fixing things instead of applying Band-Aid after Band-Aid, season after season. I'm not saying anybody is, I'm just saying we want to be tracking it over time. So that's why we make Cultra. Quick plug, you can put all this data in, it auto grabs it from your PDFs from the lab or your CSV files, and you can see if your phosphorus level is increasing or decreasing, or any of these indicators are going up or down. And you can write your recs on it. It's pretty cool. Next example, manganese. First, we look at our soil tests, right? Fall or spring soil tests. We got 38 ppm of manganese, so we shouldn't apply any, right? Let's look at our saps. We take a sap, our manganese is low. What the heck? Why do we have adequate manganese in our soil, low in our sap? There's something going on preventing uptake. A lot of times we look at our soil, pH is good. If our pH was higher than 7, then that would probably be why our manganese is low, but it's not. It's at 6.5, so we're good. Or organic matter, 1.5, that's probably slightly too low. It's going to decrease our ability for our soil to naturally chelate manganese. Another thing that can point to that specific piece is our water extractable organic carbon. If that's low, then our soil doesn't have the food for the microbes. We don't have the microbial capability to naturally create the organic compounds that chelate manganese and prevent oxidation. Now, when manganese oxidizes, it goes from Mn2+, which our plants can uptake, to Mn4+, which our plants can't uptake. That's really bad. And when our manganese goes from 2+ to 4+. To prevent that, we need to prevent oxidation. So our redox potential of our soil. When we have high WEOC and soil respiration, we increase what are called microsites, where our microbial life is using up the oxygen, right? We have microsites of a bunch of microbes that are able to create these organic compounds to naturally keep our manganese at this reduced form. So this is reduced, this is oxidized. We want to think what contributes to oxidation and how do we prevent it? How we prevent it is increasing our ability to chelate our manganese ions with our microbial life. So our microbes will produce these organic compounds that attach to our manganese ion and chelate them, meaning protect them, prevent them from oxidizing. But if our organic matter is low and our microbial life is low, then our manganese is going to be turning into this 4+, it's going to be oxidizing all day long. So we look at our Haney test, our manganese levels are also low, and then our saps, we have low manganese, and we have high nitrate. If we're applying a bunch of nitrate, just synthetic nitrate, to our soil, it increases the oxidation of manganese. So do chemicals like glyphosate, increasing oxidation potential of manganese. That's not saying it's good or bad or whatever, I don't want to get further yelled at on the internet, but we do want to make sure we're looking at our manganese levels in our sap and looking at where our bottlenecks are to prevent that oxidation from happening and how we can help our soils facilitate giving manganese in the correct form to our crops. So we want to increase these numbers because that's going to increase, you might be seeing a pattern here. We want to increase these numbers from low to adequate to increase our manganese chelation potential because our manganese is good. The amount of manganese that's in our soil is good. A lot of times it's good, and most of the time the bottleneck is here. But again, we want to figure out what do we do this season, and then what do we do to decrease our fertilizer bill for continuing seasons. So first, we probably want to do a manganese foliar application in a chelated form from a trusted source. Chelated foliar manganese is going to help our crops put more carbon into the soil. Manganese is a key component of allowing photosynthesis to turn sunlight into sugars and then move those sugars into the soil. Manganese plays a key role in that process. And so fixing our manganese this season is going to help bring these numbers up. For this specific example, we'll probably be doing multiple sap tests throughout the season, and we might not need just one foliar application of manganese. We might need to just keep track with it every month, every 2 months or so for maybe a couple seasons until we're able to naturally get our soil organic life and our microbial life up to where it needs to be to make sure that this manganese that's already in our soil can be chelated to prevent it from oxidizing. Because right now with these numbers, this manganese is never going to get into our crop. It's going to get oxidized, our plants aren't going to be able to use it. So we want to take a twofold approach. First, make sure our crop gets manganese this season. Second, make sure we future-proof our operation by getting this manganese into a form that our crops can uptake. We're going to do that through soil building practices like cover cropping and maybe looking at humic and fulvic acids or other carbon-based amendments if it fits in your operation to increase these levels so our manganese can naturally be chelated and we can decrease our reliance on in-season foliar applications. That's a pretty easy example. We're just looking at, we have plenty in our soil. If we just took a soil test, we probably wouldn't think anything's wrong. Deficiency might not even show up in our plant and how it looks, but our crop is not going to be as efficient at turning sunlight into sugars for microbes. It might be turning sugars into energy for the plant, but what we want to make sure our crop is doing is creating excess sugars. So over time, these numbers are going up instead of going down. All right, so the goal of this video is to explain how we can use our lab tests to see a more full picture of what our nutrients are doing so we know exactly where the bottleneck is so none of our fertilizer dollars go to waste. And we're making sure everything we're doing is unblocking bottlenecks rather than pushing problems down the road season by season. Is the nutrient present in the soil in the first place? We can look at some of the imbalances that can occur. Things like base saturation ratios, soil structure, and CEC, and organic matter, and pH. All of those things are incredibly important for broader systemic shifts in our system that have massive downstream effects. Then we can look at, are our nutrients becoming available? Are they being able to be entered into the soil solution, or are they bound super tightly due to issues with pH, due to issues with nutrient antagonisms? Are they in the correct form that our plants can uptake? And then are our plants uptaking them? This is the ground truth test, right? It doesn't matter if all of our levels here are high and adequate if our crop isn't taking any of them up. And oftentimes that comes down to our mineralization rates and the rates of our soil microbes to turn nutrients that are locked into nutrients that are unlocked and plant available. There are a bunch of other tools in the toolbox to figure out exactly what to do, but these are just how to use the lab tests to better understand what's going on in our soil. Now, a key thing I want to touch on is I see a lot of decisions made based on a snapshot of what is in the soil right now, rather than the direction of where those indicators are going. And so, for instance, we might have a different phosphorus management plan if our phosphorus levels are going down versus going up, even if the snapshot is the exact same ppm number. So we made Cultra to let you take all of these tests and put them into a software so you can make graphs in 2 minutes. You just take all of your tests, upload them into our software, and then you can say, what's my calcium level? What are my calcium levels doing in field 4? Or is my phosphorus going up or down in block 6? And you can click 3 buttons and you can see those directions so you can better understand exactly where your fertilizer dollars should be going. And you can make the best management decisions, not only for this season, but for next season and the following seasons. I think using a lot of these tools, in addition to just these 3, things like PLFA, things like biome makers, looking at the entire microbial species that are under our feet, to new technologies like scanners that we can scan the plant to figure out nutrients. I think all of those are incredible tools that make a lot of sense, and I'm really excited for the future of agriculture, and I'm really excited for farmers to be able to decrease their fertilizer bills over time, growing healthier crops with the best management decisions that they can do on their operation. And it's our goal to help facilitate that as much as we can, so nobody's drowning in spreadsheets trying to figure out the answers to these questions. I really hope you enjoyed this video. I had a ton of fun putting it all together. Again, my name is Jack, and I hope to see you in the next video.